Okay, your test paper should be kept ready. Let's talk about the first point. First question, why do objects fall? Why do objects fly? What keeps us stuck to the ground? And what enables helium-filled balloons to float into the sky? Okay, anybody has a suggestion? Why is it that everything falls to the ground? Okay, many things fall to the ground.
Gravity.
Gravity? Okay, so what exactly is this gravity? Huh? It is a pull. Oh, your physics teacher very good, huh? So what exactly is a pull? Okay, it's a force. It pulls us to the ground. So when we in our everyday lives, we see things dropping. Instead of saying things are dropping in physics, we say that there is a pull by who? By what? By the earth. The earth is pulling everything downwards, including the girls talking at the back. The earth is pulling you downwards, that's why you're not floating away. Okay? Now, what about helium-filled balloons? Why do they float then? Why aren't they pulled to the ground? Less dense. Why do they float? Less gravity? Water density? No. Density of helium? Okay. Have you all learned this word density before? When? What do you all learn in primary school for density? Did your teacher tell you how to calculate? Then we will learn that. Okay. So these are the outcomes. It is in your notes, so please read them. Now, if somebody asks you, what is your weight? What will you answer? Something. I want the last word. What is the unit you will use? Okay, let's assume that we are all physics students. What is the unit you will use? Newton. Okay. Let's assume we never learn physics at all. What is the unit you will use? Kilograms. Okay. So in layman, in everyday life, when somebody says what's your weight, they are referring to what is your mass. So in this topic, we'll talk about the difference between weight and mass. Okay, but for now, the good physics students, you know that weight is actually a force. And when somebody asks you for your weight, as a physics student, you must say the answer in newtons because it's a force. Okay, so kg, this is what is written in your booklet. But force, because weight is a force, forces are measured in newtons. So we shouldn't be measuring them in kilograms. Okay? Weight, we also know it as gravitational force. Mentioned before in the previous topic already. And a force is defined as a push or a pull. On Earth, when we talk about gravity, it is a pull towards the center of the Earth. No, not pushing, it is pulling you. Now, when somebody goes out to space, you imagine all the space movies that you watch. The astronaut is in the floating around in space. He's in the space shuttle. He's in a space station, whatever. Is he walking or is he floating around? Floating. Yeah, he's floating around. Why? Why isn't there anything pulling him to the ground? By right, us on Earth, right, we are being pulled to the ground. So why isn't he being pulled to the ground? Something about gravity. So what about gravity? You mean no gravity? Gravity is less strong. What else? No, not that. So you see, they are floating around because they are experiencing low weight. In this case, at an extreme end, when they have no weight at all, it's called weightlessness. So imagine the astronaut floating around. You ask him to stand on the weighing machine. Will he give a reading? No, right? The weighing machine will be floating around with him also, right? There is no reading at all. There is no weight. He is not experiencing a pull to the ground. Okay? Because he's very far away from the Earth. When astronauts they go to the moon, are they walking or are they floating? On the moon, okay, let me rephrase. Are they walking very strangely or are they floating? Okay, how are they strange when they walk? They look like they're just bouncing slowly in slow motion, right? They're bouncing in slow motion. Why?
Because there's a lot less gravity.
Yes, because gravity is less on the moon. So I explained to you before that it's because of the mass of the moon. Yes. The sun? Yes, it has gravity also. So on the moon, because there's less gravity, your weight is less. You divide, let's say your weight now is 600 newtons. Incline 60 kilograms. Let's say you are 60 kilograms. So your weight is 600 newtons. When you bring yourself to the moon, do you lose any protons, electrons, neutrons?
No.
You don't, right? Do you gain any atoms and molecules?
Unless you eat a lot.
Okay, let's say you don't eat a lot. Let's say we don't eat at all. Okay, we just go there. Does your mass change? Your 60 kilograms of you made out of the atoms. Do you lose any atoms, molecules, all that stuff? No, right? So when you go to the moon, you are still 60 kilograms. But on Earth, you being 600 newtons, when you go to the moon, you will now be 600 divided by 6, you get 100 newtons only. So when you stand on the weighing machine, it will show you 100 newtons. As though your mass, which was 60 kilograms, divide by 6, as though your mass is now 10 kg.
Because the gravity is 6 times lower.
Yeah, the gravity is 1/6 times of Earth. Okay? That is why the astronauts, they appear to be moving in slow motion, bouncing up and down. Because the acceleration on the Earth is stronger than that on the moon. On Earth, you jump down from the table to the floor very fast, right? From this distance, jump down very fast. On the moon, you appear to be slow motion. Well, it takes some time to drop down. Because gravity is lower. Yes? Any questions? Okay, so that's what's happening. So mass, mentioned a few times, it is the amount of matter in a body. What is matter? You learned that in primary school. What is matter? Yeah, so they occupy space, right? When we talk about matter, we are referring to atoms and molecules. Even air is also matter, right? Occupies space. Mass is a scalar quantity. That's why every time I talk about your mass, I will be talking about your atoms and molecules. It is scalar. There is no direction. If you have 60 kilograms as your mass, there's no direction to talk about. Whether you are here, there, anywhere, you will still be 60 kilograms. The unit for mass is the kilogram. So now what's weight? Weight is the gravitational force acting on a body. It is a vector quantity. So the very first difference that we can see is that one is a scalar, one is a vector. Scalar, no direction. Vector has direction. In fact, weight is a force. So we need to state the direction of the force. So since weight is the gravitational force acting on a body, it tells us that when the gravitational force, when you go to a different planet that has a different gravitational field strength, your weight is going to change. Okay? When you go to the sun, your weight is going to change. But before your weight changes, you'll be burned up already. When you go to the moon, your weight will also change. You go to Jupiter, your weight will also change. If you climb up the highest mountain on Earth, your weight will also change. How? How will your weight change? So think about it. Tell me whether as you climb up the highest mountain, your weight goes up or your weight goes down. Up or down? Who says up? Who says the weight goes up? When you climb the mountain, does your weight increase or decrease? So let's try again. Does your weight increase when you climb the mountain? Okay. Does your weight go and go down and down and down, very, very deep. Go underground very deep. Will your weight increase or decrease?
Increase.
Who says your weight will increase? Okay, correct. Your weight will increase as you go closer and closer to the center of the earth. So the SI unit for weight is the Newton. Next thing, gravitational field. It's very difficult to imagine what a gravitational field is. So I will use something that you're more familiar with. What kind of field are you familiar with? Besides the school field. Magnetic field. When you were in primary school, did your teacher make you draw magnetic field? No? Did your teacher give you a magnet and then give you some iron foulings? Yes, right? So for those of you who have done it, north, south, then you throw the iron fillings on it, then you shake, shake, shake. So you will see patterns like this, right? You see these things, right? These lines over here, they represent the field. It is invisible. We cannot see the field. Just like on Earth, the Earth we are experiencing gravity because we are in the Earth's field, okay, which is invisible. I can't see the lines popping out from the Earth, but I know I'm being attracted to the Earth. That's why I'm not floating away. Just like a magnet, there are these lines over here that are imaginary. They represent the field. That is why when you put another piece of magnet over here, it is interacting with the field and you will get attracted to it. Okay? Once you put it very, very far away, the field is very weak. So do you experience the pull? Unlikely. Because it's very, very far away. It's the same thing as the Earth. We change this to the Earth. This is our Earth. And this is us. Okay? You are attracted to the Earth because you are near to it. The further you move away, the less weight you will feel. Okay? Smiley face represents you. Okay, these lines over here, they represent the field. They are just telling you that if you put an object over here, it will go towards the center. Okay, whether you are at the bottom also, you will go up to the center. That is, okay. So, us being at the equator, right, we are all in Singapore. If this is the Earth, this is the equator. You guys are here, right? Right? You are actually kind of sideways. You realize that? Then the people in, let's say, Japan, then they are less horizontal. Then the people in Australia, they are kind of upside down. But when you take a plane to Australia, then you land at an airport, you step out of the airplane, are you upside down? No, you're still upright, huh? Why is that so? Because the Earth is very big. It feels like this is a flat ground. This also feels like a flat ground to us. This feels like another flat ground. We are all being pulled to the center, all of us. We are experiencing gravitational force towards the center. That's why we always remain upright, regardless of where we are. Okay, as you go further and further away, the gravitational field strength gets weaker and weaker. Just like the magnet. As you go further and further, the field gets weaker and weaker. So same thing for the Earth. Go further, you feel less force, which translates to our weight. So it is the strongest at the surface of the Earth. Okay? That's why when you climb a mountain, you are no longer at the nearest to the surface of the Earth. So your weight will drop a little bit. Okay, Earth's gravitational field strength. Although we say that the field is getting weaker and weaker, for our syllabus in O level, we are not going to consider you climbing a mountain. we just consider everything is near the surface of the Earth. Even if we tell you a question, 10 stories high, you still take it that it is very near the Earth. Because the Earth is so big, right? When we talk about very far away from Earth, we are talking about maybe something like this distance away. Okay? That is very far away from Earth. That's significant. But for us, when we talk about 10 stories high, it's probably going to look like this only, isn't it? 10 stories high on the Earth is just a small increase in distance. So it is insignificant. Remember your significant figures in maths? What significant means? Not important. Okay? Insignificant. So as long as you are near the Earth, 10 stories high, 20 stories high, all these are considered near the Earth. Okay? You will not be put in a situation where you have to think, oh, is the teacher testing me near or far away from the Earth? No, everything is near the Earth. Unless you say it's space. In space, then it's obviously far away from Earth already. Okay, gravitational field strength. What is the definition? Here, put a star. Write down, may be tested. Is it written for you already? Gravitational field strength is defined. Yeah, okay. So it is already given to you. Don't need copy, but put a star. Highlight it. Okay, now this is one of the key points of this lesson. On Earth, every 1 kg of mass in an object experiences 10 newtons of gravitational force. If it is a 1 kg mass, it will experience 10 newton force. Okay? If it is a 2 kg mass, what will be the force experienced? 20 lah. If it is a 10 kg mass, what is the weight that you experience? 100. So now for your own mass, your mass will probably be what, 45, 50, whatever. So that's why you multiply by 10. That's why I tell you to multiply by 10 and you get your weight in newtons. So this means that the gravitational field strength, okay, see based on the first point, 1 kg experience 10 newtons. Therefore, the gravitational field strength is 10 newtons per kg. Everybody say with me, 10 newtons per kg. 1, 2, 3, go.
10 newtons per kg.
So 1 kg experience
10 newtons.
10 newtons. That's what it means per kg. 1 kg experience 10 newtons. So on Earth, 10 newtons per kg. So we use this letter little g to represent the gravitational field strength. In our questions, we will be given G equals to 10 newtons per kg. This one over here refers to the gravitational field strength. Okay, little g is not a capital G. Okay, I will stop at this slide. W refers to weight. Weight equals to mass times gravitational field strength. What does the little g over there represent? Gravitational field strength. How much is it? 10 newtons per kg. So to calculate your weight, W equals to mg. For Mr. Wall, my mass is 70 kg. I multiply by 10, I get 700 newtons. Okay, so that's how it works. Simple, right? Just times 10. On Earth, so we will stop here.